Can you handle the pressure? Because today, this math, it isn't just numbers on a page. It's the literal difference between a system holding strong and completely falling apart. Welcome back, future doctors and engineers, to a brand new explainer. Today, we're not just finding limits, we're fixing broken functions, testing structural integrity, and honestly, we're staring right into the infinite horizon. You ready for a new mathematical thrill? Let's get into it. All right, jumping right into level 1, the engineering stress test. Let's ground this in some reality, okay? In structural engineering, if the math that models your building's wind resistance has a sudden jump, or even worse, an infinite discontinuity, well, what does that actually mean? It means the structural stress goes completely off the charts. The building literally collapses. You absolutely need continuity to survive here. Those equations just have to connect seamlessly. But hey, before we start welding these mathematical fractures back together, I've got to give a massive shout out to the community members topping our Calculus Heroes leaderboard from our last challenge. I mean, seeing you all tackle these rigorous problems is exactly why we do this. So let's look at trial 1, welding the break, straight out of section 2.5. Here's how we actually execute that weld on a broken piecewise function. So our function changes its rule at the critical stress point, where x equals 2. By taking the left-hand limit and setting it strictly equal to the right-hand limit, we literally force the math to connect. We just substitute x equals 2 into both sides, and that leaves us with a really beautiful, straightforward algebraic equation. 4c plus 4 equals 8 minus 2c. Now, by isolating c, we find that 6c equals 4, which simplifies perfectly to 2/3. So, by ensuring our constant c equals 2 over 3, we've successfully welded the break. The function is now perfectly continuous. Boom, you've passed the first stress test. Moving right along to trial 2, the infinite horizon from section 2.6. So what happens to a system when you push it to its absolute extremes? Well, we're faced with this massive infinite square root fraction. To solve it, we systematically divide the top and the bottom by the highest power of x. And when we bring that x inside the square root, it turns into an x squared. Now, as x gets infinitely massive, those smaller fractions, they just dissolve right down to 0. And as those smaller fractions evaporate, all the complicated noise of the equation just kind of disappears. The math cleans up beautifully, leaving us with a solid structural limit of 3 over 2, meaning no matter how far out into that infinite horizon you go, the system stabilizes right at 1.5. But beware the trap. Stewart's text explicitly warns us about a really common pitfall here. If x was heading to negative infinity, the behavior of that square root extraction actually changes, because the square root of x squared is the absolute value of x. So if x is negative, you must introduce a negative sign when you pull it out. Watch your signs at infinity, seriously. Speaking of limits at infinity, let's just pause the explainer for a second. Think about this mid-test challenge. If a function's limit settles precisely at y equals 3 as x goes to infinity, what is the geometric equation of its horizontal asymptote? Post your equation down in the comments right now before we continue. Okay, incoming digital glitch. Warning, lies my calculator told me. Sometimes the very technology you rely on to test these structures is totally lying to you. I like to call this the vertical mirage. You look at the screen, and your graphing calculator draws a nice, solid line. But if you actually analyze the function analytically, the rigid rules of calculus prove there's a critical hole right at x equals 2. Why? Because at that exact point, the function evaluates to 0 over 0, which is an indeterminate form. The calculator basically just skips a pixel, hiding the mathematical truth. Stewart's text reminds us of a really vital lesson here. Human understanding of foundational math is always going to trump a calculator's crude pixel approximation. Your machine doesn't know about limits. It's literally just plotting dots. So don't let the pixels deceive you. Let the rigorous math guide you. All right, let's tackle trial 3, the IVT bridge, checking back in with section 2.5. Our final foundational check is the Intermediate Value Theorem, or IVT. You can kind of think of this as the ultimate test of a continuous bridge. Let's test it out with a polynomial x to the 4th plus x minus 3. Because it's a polynomial, we know it's a perfectly solid continuous bridge, right? So, testing our starting point at x equals 1, we get a -1. But then, testing our endpoint at x equals 2, we jump way up to a positive 15. Now, just apply the logic here. Since 0 sits perfectly between -1 and positive 15, and our bridge has absolutely no breaks, the function must cross the 0 line to get from the negative side to the positive side. It can't just teleport. Therefore, by the Intermediate Value Theorem, a root absolutely exists somewhere between 1 and 2. I mean, that right there is the immense predictive power of continuity. And finally, the final boss, the ultimate infinity puzzle. All right, you've survived the stress test, you've welded broken functions together, and you dodged those sneaky calculator traps. But to secure your spot on the next leaderboard, you gotta face the final puzzle. When evaluating limits at infinity is the ultimate answer for our mystery challenge, 0, 1, or infinity. Solve the puzzle below, grab your Group 2 cheat sheet, and get yourself ready for our next explainer where we tackle the derivative as a function. Thanks so much for joining me for this deep dive into Stewart's calculus. Remember, you guys, it's not just about getting the right answer. It's about understanding that deep, continuous logic beneath it all. So like, share, stay dynamic, and above all else, always trust the math.